right, so Storage Developer Conference will come to an end today. And after a great series of lectures, you're going to your office tomorrow. You see this email in your inbox saying, hey, the server that you've been long waiting for, fully loaded with persistent memory, has arrived, and it's been racked in the data center lab. Please go ahead and configure a server so application developers can start doing their work. By the way, they also asked you to run some performance benchmarking on this persistent memory aware server so they can baseline their performance when they do their application. So you go into the data center lab, you power up your server, you're in the operating system. Now you're wondering, have the DIMMs come provisioned? What are the tools available to provision? Are they part of the operating system? Do I really need a vendor-specific provisioning tool? By the way, what are those benchmarking tools that are persistent memory aware already? And so on, right? A lot more questions. So as a system administrator or an application developer, this is the presentation that will help you get started on persistent memory, what are the tools available, and also how to use them. So I'm Usha Upadhyayula from Intel Data Center Group, and I have my co-presenter, Steve. So we'll be going through, where's my pointer? Sorry. We'll be going through a list of persistent memory tools, configuration tools, benchmarking tools, and analysis tools. And then Steve will walk you through some of the tools and give demo of how to use these tools. But first, what is persistent memory? If you have not had a chance to attend Andy's talk this morning, I just want to put a slide up there so that we're all on the same page. So persistent memory is byte addressable like DRAM, but it retains its content like storage. And it's cache coherent. You can do load store access. But why does it really matter now? There have been NVDIMMs in the market for some time. So with DIMMs that are powered by 3D crosspoint media, we have much larger capacity than DRAM, higher endurance, and lower latency than SSDs. And that's creating a new tier in the industry, basically between the DRAM and the block devices. It also has the ability to do in-place updates, which basically eliminates page caching. And you don't have to do kernel, you don't have to go back and forth into the kernel. And it also has the ability to do DMA and RDMA. So here are the list of tools that we put together. From configuration and provisioning tools perspective, there are a lot of vendor-specific and vendor-agnostic tools. At the pre-boot level, we have a tool that is created by Intel, and it is specifically written to be able to manage Intel 3D crosspoint-based DIMMs. It's called IPMCTL. This is an open source tool, but it's specifically written for Intel persistent memory DIMMs. It's cross OS. It works in Linux, it works in Windows, and also in ESXi environments. There is also a Linux tool called NDCTL. Again, this is specifically written this is a vendor-agnostic tool, and it works with any NVDIMMs. I'm not as familiar with Windows as Linux, but IPMCTL works on Windows as well. But there are certain PowerShell commands that are created to be able to provision the persistent memory DIMMs from Windows environment as well. From benchmarking perspective, I'm not sure how many of you are aware of already the Intel memory latency checker that has been enabled to work with persistent memory. We have another slide coming up. We'll go a little bit more details into that. FIO, we've added few IO engines that can generate and understand the persistent memory and can generate the IO to persistent memory. PMEM Bench is a developer benchmarking tool. If you're writing an application based on PMDK, if you're updating the code for PMDK or you're modifying the code, this is the tool that helps you kind of look and see if you have introduced any regressions. From the analysis perspective, VTune amplifier has been modified to enable for persistent memory. There's a new tool called Intel Persistent Inspector. Basically, what this helps is identify persistent memory programming errors. What that means is that Andy and others have talked about how flushing is important to make sure that the data is durable and has reached the power fail safe domain. So the tool basically helps you identify if there are missing flushes, if there are redundant flushes, or if there have been some reordering. So you've actually updated, you have done a store, you haven't really flushed it all the way to the durable region, but you have actually stored done another store on it. So this is the tool that actually helps you identify those and provide some recommendations. Intel V2 Platform Profiler, this is another tool that helps you understand if there are imbalances. Are you using your hardware properly? Is there anything that you can do with your application to make sure you take advantage of the performance of your hardware? The PMEM pool and PMEM check, these are basically for applications that are written on top of or using PMDK. So persistent memory pool is an offline analysis utility that will help you look at the pools. Again, we're going to talk about what these persistent memory pools are, but it'll help you look at your pool, persistent memory pool, and also check for any data consistency errors. You can dump the user data and then basically look at how you can repair the data as well, and many more. PMEM check is very similar to persistent inspector, but it is based on the Valgrind framework. So again, it helps you with detecting persistent memory related programming errors, similar to what I just talked about for the persistent memory, but again, that's based on Valgrind. This was originally written to validate PMDK, but it can be used if you write a program outside of PMDK as well. And we had to make changes to Valgrind also, so it's persistent memory aware. So before we move on, just want to make sure that the tools that are written and the other things that are around persistent memory programming are all based on industry standards, and here are the standards that we use when creating the tools. Okay, so before going into what are these tools and how to really use them, there are certain concepts that we need to understand. So when you have persistent memory raw capacity, you need to basically divide them into something called regions. So regions can be created in an interleaved manner. So they can be one-way interleaved or they can be n-way interleaved. So here we have an example of 4 DIMMs. And here we are showing that in the first diagram, on the leftmost side, we show that the region can be created 1 per DIMM, or it can be interleaved across the 4 DIMMs. So when you create a region, all that it's doing is creating a contiguous memory. So when the reads and writes are done striped across a contiguous memory. But creating a region doesn't really expose that to the application. You need to do another step, just like on SSD, that creates something called namespaces. So namespaces now generate a physical, the logical device, so applications can do their I/O too. So these are the fundamental concepts on which persistent memory is provisioned and then exposed to the application. Now, I talked about IPMCTL and NDCTL. So there are a lot of common supported functions from IPMCTL and NDCTL for provisioning. So you're able to create regions, namespaces, you can enable, disable, destroy, all that, but you really need IPMCTL to create the initial regions on the raw capacity of Intel Optane DC persistent memory. And again, it's available at the user space as well as at the pre-boot level. And it's available across different operating systems. In addition to provisioning commands, the tools also provide monitoring and maintenance support. So you can look at the health of the DIMMs. You can inject errors. And IPMCTL also provides you way to set security policies. You can set, when you create a region, you can actually set a passphrase so it's much more secure and things like that. So now we talked about, I have a persistent raw region. I've divided them into, things that operating system has created these logical devices. Now applications need to talk to. But how can we make application developers' life easier to talk to these logical devices? So persistent memory development kit is built on top of SNIA programming model. And we have created a bunch of libraries. Some low-level, for low-level support, some of them have transactional support. We have several language bindings. And it's basically a set of user-level libraries that allow you to be able to allocate memory from persistent regions. And then, again, as SNIA programming model says, it's memory-mapped region. And then you are able to do some, can be abstracted from all the details of what do you need to do if you want to update data structure that is larger than 8 bytes. So we provide transactional support, and at the low level, you don't have to worry about the nitty-gritty details of, okay, is this flush command available on the platform? All those things are abstracted out for you to make it easy to adopt persistent memory programming. And it has C++ support that is production quality. There are few other that are coming in the pipeline. There is a Java support, and at different levels. We have low-level support for Java and the container support, but they're all right now labeled as experimental. The dark green box that I show, it's labeled as volatile memory. But I've been talking about all along about persistent memory. What is that doing over there? So we've added support for persistent memory as part of a kind for libmem kind. So you can basically use libmem kind to allocate areas on persistent memory that could look volatile. Meaning, if you have certain transient data structures that you really don't want to persist, you can use libmem kind to create that volatile region, which will go away across the boots and application if the application doesn't really need to persist. So that's something that's not part of PMDK, but it is enabled in libmem kind, and it's available. So again, just to summarize, we've started from at the bottommost level of raw memory capacity. We build them into regions, into namespaces, and there are two different ways applications can access persistent memory. One is through file system DACs, and that's where PMDK comes into picture through persistent memory pools to abstract it even more to the application developers, so they don't have to really worry about the memory mapping of the files or other transactional things and stuff like that. The other thing, the other way for application to access persistent memory is through device DACs. Again, there is no file system involvement in here. You get direct access to the device that is created as in device DACs mode. So what are persistent memory pools? So we talked about memory mapping of the files and how PMDK exposes it. So persistent memory pools are a way of exposing a single or set of memory mapped files as a pool for the application. So an application can create different memory mapped files, and again, those different memory maps files are shown up as pools. And then it's only intended to work with DACs file systems. So basically, how do you identify, if your application crashes, you come back up? How do you really need to get back to the data structure that you're working with? So you kind of give the pool ID, and from the pool ID, there are different ways of getting to the root of the pool, and then you can get your data structures that you've been working with. So that's the end of how you provision your DIMMs and how you really expose your persistent memory to your application. So from benchmarking tools perspective, again, memory latency checker is something that when you run it, you can run it without any parameters. When you run it, it looks at the topology of your platform. It generates the latency and bandwidth information. You can change the loads on your system, and then it generates latency and bandwidth, how they change with the change in the load on the system. We've added support for persistent memory in the sense that you can provide the mount point, the memory mapped mount point to MLC, or a memory mapped file, and then it basically runs the latency and bandwidth happening to that memory region and generates the numbers that way. So from FIO perspective, there have been 3 different IO engines that are added, called libpmem, devdax, and libpmem block. So what this basically does is when you start your FIO with this IO engine, it uses the libpmem API that is part of PMDK to do IO to the memory mapped region. Again, PMEM bench is more for developers, so that's when you really are contributing to the PMDK code. I'll let Steve take over from here. He'll do the analysis tools and then do a walk through the tools and do some demonstration.
Yeah, thanks, Usha. So I'm going to look at the analysis tools, of which we have quite a few. So we already mentioned these persistent memory pools. We can create them using the APIs that are available, but the PMEM pool was really designed for offline administration of these things. So we can print information about them, we can create them, we can do data validation of our metadata using this type of stuff. We can dump out your user data. It's not really meant as a backup tool per se, but we can do some forensics on that data to figure out where things may have gone wrong. And we can remove them and convert them. Convert means we're going to upgrade to the next version of our pool metadata. So this information is available. Source code is open source. And again, it's available on anything that supports PMDK, so whether it be Linux or Windows. PMEM check is not the same as PMEM pool check. PMEM pool check checks your metadata of the pool itself. PMEM check, as Usha said earlier, actually checks your application. Are you doing flushes in the right order? Are you doing them often enough? Are you not doing them in the correct order? So again, we support Valgrind, Hellgrind, and memcheck, so you can run your application under these virtual machine engines. It's not going to give you the best performance for your application, but we're here for consistency checking, right? We want to make sure that your data gets down to the media in the right way. So we can log all the persistent memory operations for post-analysis. And we give you a nice little summary of saying, this integer isn't made persistent, you might want to go back and put a flush in here or whatever. But again, the idea of PMDK is that all of this is done for you, right? So you don't have to worry too much about it. And we do it similar to database transactions. Again, that's a recurring theme with PMDK and most of our libraries is that they are transaction-based, right? We're going to get you down to a consistent state using known partially acid operations. So again, we have the vTune suite, which many of you may be familiar with. And within that, we have amplifier. So the amplifier takes your application and instruments it and gives you some really nice results about what you're doing with it, where your hot data structures are, where you can improve your code. I mean, it's not going to tell you exactly which line for line, but you can get down through code if you compile your code with symbols. And we'll tell you roughly where your optimizations could be within your application for persistence. The platform profiler is a more holistic view of the physical hardware. So it'll tell you what your CPUs are doing, what the back-end persistent DIMMs are doing, what your DDR DIMMs are doing, and you can see whether your workloads are working or will work for a persistent world. The persistence inspector is similar to the PMEM check in as much that it'll analyze a running application and give you really useful information, again, about where your hot data is, whether or not you should be moving that hot data to DRAM, or whether you can kind of move it off to persistence because it's slightly cooler, you don't care about it too much. And then the advisor is an interesting tool. It was really designed for vectorization, but there's been some additions here where we can do memory access profiling. So you can really see now, almost down to an address level, where your hot areas are. And again, all of these tools together will give you a really good understanding of what your applications are doing and where you can make improvements. All of this stuff's available for download. You can go to the URL at the bottom. Persistent memory, we have tutorials, videos, loads of really cool information about, not necessarily using all of this stuff yet, because that's coming. But the Studio 2019 is in beta right now. So you can go, we encourage you to go download it, play with it, and ask questions to us. All right, so provisioning. This is kind of the meat of what I wanted to get to. So we've introduced the kind of the concepts, the terminologies of your namespaces, your regions. What does that really mean when you're at the terminal, right? You need to type this stuff in. You might be using Ansible for remote replication or remote distribution of your systems. So I want to walk through what you would type at the keyboard to get this stuff working with your applications. So I'm going to walk through a couple of example configurations, the common configurations that we see. It's going to be Linux-based, so apologies for the Windows guys, but it is going to be pretty similar. And this works whether or not you have physical DIMMs in your box or you're emulating this stuff using DRAM or some fast SSD if you're using some kind of virtualization topology. So we start here at the bottom. This is just a single case, and all my examples are per socket, right? So whether or not you've got a 1 socket, 2 socket, 4 or 8, it doesn't really matter. So we use our IPM create command to create what we call a goal, which gives us our region. This is no different than DRAM, effectively. Layered on top of that, we just create a single namespace of the same size or as close to the same size as possible for our region. Here we just use the NDCTL create namespace command. Nice and easy. So that gives us a device called PMEM0 under our dev directory on Linux. And then on top of that, we can just use either the ext4 or the xfs, makefs commands to create our file system. Now the important bit here is that when you mount it with a -o DAX flag. So that's the only difference here. And that tells the kernel, hey, look, this is a DAX-enabled file system. I'm going to bypass all our page caches and go straight down to the media. Now, because this is DAX file system, we are going to create our PMEM pool on top of this file system, and this is what the applications will memory map. So this is a nice, simple configuration, nothing too hard here. All our DIMMs are interleaved at the bottom. So we get a really nice namespace. So the purpose of this one is that we can now split these interleaved DIMMs that have a single region, and we can split it, in this case, in half. So now we use the same commands as before, but now we just specify the size when we're creating our namespace. Right? And you can specify these. There is a minimum size. Most people are not going to use that. And the naming convention here is the first decimal number of the namespace itself matches the region of which you created it on, and then we just increment the minor number to say how, this is 0, this is 1, this could be 2, 3, 4. It doesn't really matter. And each one of these gets their own dedicated device in our device file system. And again, on top of this, we can just create a regular file system, ext4 or xfs. Again, mounting it with the -o DAX flag, that's the important bit. And then we can create a single persistent memory pool on each one of these. So this might be useful for some applications that don't want 384 gigs worth of persistent memory in an application. You might only want 192. And there's really no limit to the number of namespaces that you can create here. So if you want smaller namespaces, that's fine. Just create as many as you need. Yeah?
So those all correspond, meaning there can only be one namespace, one PMEM1, that you can't have two DAX file systems on top of.
You can.
Oh, you can. Okay, so it can sort of branch out.
Ta-da!
Wow, perfect.
There you go. Great question. So yes, and this is where I'm going with these, and there's one more after this. So here, we can now take this namespace from the previous example. We've still got our two devices. We now use standard file system partitioning tools, such as McPart, FDisk, gparted, whatever is your favorite, and we can further partition these again. And on top of these, we can create more persistent memory pool. And again, there's no reason why you would need to create a persistent memory pool that's the same size as either your DAX file system. You can specify the size here and create smaller persistent memory pools per file system. So we've talked about FSDAX, we've talked about device DAX. Here we're just showing that you can do it on the same region. Right? So it's another mix for optimal configurations. And the difference here is that when you create your namespace, the default is to create a file system DAX namespace. But if you specify the mode as being dev DAX, you actually get your device DAX device being exposed further up. So there's nothing different too much there. And then here, we get rid of interleaving on our DIMMs. And so we don't care too much about interleaving, but we can now, per DIMM, we get an individual region. And the only difference here is that now we say that the app direct is non-interleaved, right? So our regions are no longer interleaved using the DIMMs. Everything else is the same. We can create two namespaces, two file system DAX, one device DAX. So once you've kind of got to persistent memory pools, all right, how do we create those? Well, I've given you a couple of examples here of how to create them. Yeah?
I wondered why you would have different regions, but not separate DIMMs for each region.
Why you would not interleave them?
Why would you do that?
Well, in a virtualization world, do you really want to lose, all of your stuff? I mean, if one of these DIMMs should fail, in the very unlikely event that it ever will, you would effectively lose all of your 384 gigs worth of data, right? And you could affect multiple guests on your box. Whereas if you're happy to live without the performance of interleaving, then if one of these DIMMs was to fail, you would only affect the guests using that DIMM. Or you could just go in and replace it, and you'd have to rebuild this, obviously, but you have to rebuild your guests anyway. So here's a real-world example of creating a 4 gig pool using a layout. And the layout is, as Usha mentioned earlier, that you have object pool, block pool, and log pool. Right? And those map to our PMDK libraries. So depending on which features you want, you would create a different layout for that. Now, the name, my layout, is really the tag that we talked about previously. So this is how you can individually identify which pool belongs to you and make sure that when you open that pool that you know which data structure points to your data. So once we've created this pool, we can just do PMEM info and dump out some semi-useful information depending on what you want to look at. But this is the metadata that describes this pool. Now, I just created it, so there's no real data in there yet. But this is the type of information that you can get out of this thing. So we get the UUIDs, we know which endian it is. And there's because it's an object pool, there's some object-related header information down here that PMDK knows about and knows how to access the data from there. Now, if there was data in here, you can use the -s flag, and you can get more statistics, right? So how full is your pool? How much space is available? And a few other interesting bits that might be useful to application developers, right? So when you're allocating data to this might be useful to you. Now, we haven't really introduced it too much, but there's a thing called pool sets. So going back to some of these examples where we have maybe multiple pools on different namespaces and different regions. Now you can say, well, I want to create a persistent memory pool on region 0, but I also want to might replicate that data to a pool on region 1. So how do you do that? Well, that's where persistent memory pool sets come in. So it's just a very small configuration file, and you can say, I want to replicate my data locally to a different region, or I might want to replicate it to a different host. All right, this isn't the same as RDMA. It uses a slightly different mechanism, but there is the option of data replication using PMDK. So, real demo time. Real demo. Cool. So, in the interest of live demo failures, I recorded this earlier. Yeah. I should have said I didn't want to wait for the reboot, but so this is me working with these DIMMs on my lab box back at Intel. So we're going to work through a couple of those examples. Now, this stuff's really fast, so we're going to go quickly through it in the interest of time. But I'm going to hopefully kind of keep up with myself with... let's go back one. Previous. All right, so let's keep up. So here's my DIMMs, IPM CTL show topology. I've got 3 DCM PM DIMMs in there and some regular stuff. I don't have a goal yet. So I'm just going to create an app direct goal which says, okay, well, you've got 3 DIMMs in there. I'm just going to go off and create 2 regions, right? It knows because 2 are on socket 0, 1's on socket 1. So after a quick reboot, we can show the memory resources, showing we've got 749 gig of data. We've got our 2. Let me slow this down just a little bit. All right. All right. So after a reboot, we get our resources, 750-ish gig of available capacity, and 2 regions. Again, 1 on socket 0, 1 on socket 1. One's interleaved and one's not interleaved. Okay. There we go. Are they going to play? Right. So NDCTL. This isn't my laptop. Okay, so NDCTL, this is the Linux utility that shows you, with the -D, shows you the DIMMs. We call them NVDIMMs. But you can see the UUIDs for each of our DIMMs that matches what IPM CTL was trying to show us. All right. Now we can list the regions using the -R flag. So again, this is what our goal created for us. We've got 2 regions based off of the configuration. Let's go forward a bit. Now, -N shows us the namespaces. So you can see we're kind of working up the layers here with our diagram. So in the previous example, we didn't have any namespaces, right? So when you do IPM CTL create goal, you get your regions and you get your, you just get the regions and you get the DIMMs, but you don't get a free namespace. That's up to you to create, right? Everything else is done at the hardware level. This is the software level. So the IN says, show me stuff that is either disabled by me or by the hardware or that doesn't yet exist. So that we see 2 namespaces here. They're kind of placeholders, seeds as we call them, for creating 2 namespaces. So if we just run ndctl create namespace, we get back a namespace. Now this one just so happened, because I didn't specify which one of these 2 namespaces or regions to use, we just get back the first one that it decided to use, which was namespace 1, using region 1. So this is my 500 gig namespace. forward. All right, so now here I purposefully create a namespace on region 0. I could have done this to begin with. I was just too lazy. So, and here we go. So this is my 256 gig namespace. Now the default mode for this is FSDAX, as I mentioned before. Again, you can specify which mode you want when creating these namespaces. And now that we've created namespaces, I can now list my namespaces. So here we have namespace 1 and namespace 0 with the respective modes and sizes. All right, so what happens if we created our FSDAX namespace and now we said, oh, that was a goof, let's change it to a device-DAX namespace? Well, you can destroy it and recreate it, that's fine. But we offer this force option, and the E is edit. So we can change our mode from FSDAX to device-DAX. And it just goes off in the background and effectively changes all the metadata, destroys it, recreates it, and you end up with a device-DAX namespace. And once it's done, it prints out this useful information, say, hey, look, yep, I worked, and here's all the information related to it. So if we just list the /dev and look for PMEM and DAX, we end up with what we expect, right? We've got DAX 0 using namespace 0 and PMEM 1 using namespace 1. And this is what the application can then mount, right? So we can use that with PMDK. And then all we do is create a file system on top of our dev PMEM1. So this one is just an ext4 file system. We create a mount point directory for it. We mount it, again, using the -o DAX flag. That's the really important bit we need to keep re-emphasizing. And there she is, at the bottom of the list of a regular DF output. So now we can create our persistent memory pool on top of our DAX file system. And here I'm just creating a 10 gigabyte persistent memory pool. Nothing too special here, no pool sets. And then I just print out the PMEM pool info that we saw earlier. So again, this is just a blank template, shows you all the metadata that gets created initially. So the purpose of our talk here was to introduce you to the tools, introduce you to what to do when you get your hands on the keyboard. So what we did was we just kind of overlaid the tools on top of the SNEER programming model to show that we have really good coverage of all of this stuff. All right? And we're not trying to replace any of the existing tools that you guys are used to. What we're trying to do is introduce new tools into your toolbox that you can go off day one today and go and play with this stuff. Like I say, you don't even need physical hardware. You can go off and emulate this stuff. And I'll talk about that, of how you can do that in a minute. So resources, we live PMEM.io, that's our homepage for Persistent Memory Developer Kit. The source code is all available at these links. We have a really active Google group. So if you have questions about PMDK, about persistent memory in general, come join us, go ask your question here. This is all linked from the homepage of PMEM.io. We have an IRC channel as well that's fully monitored, mostly during the Americas hours, because that's when Andy and I are online, but it's all good. The Intel Developer Zone is a really good resource. We have some colleagues here that are writing content on a daily basis of how to get you guys started with all sorts of really interesting stuff. So we mentioned the LLPL, the PCJ, the low-level persistent collections for Java. There's tutorials on there. There's tutorials on PMEM.io in the blog section. We introduce you to PMEM pools. We introduce you how to use PMEM pool sets. There's tutorials about programming this stuff. Tons and tons of information, which is really good for something that we haven't shipped yet. So NDCTL, that lives on PMEM.io. So you can go and have a look there. IPMCTL lives in its own little repository on the Intel GitHub site. libmemkind has its own website. You can go and have a look there if you are interested in using the memkind library to do volatile accesses. We have linked to the SNEER NVM programming model of where all this stuff came from. But I would probably encourage you to go to docs.pmm.io. I mean, that's something that we've been working on, I've been working on for quite some time. It's got some pretty good getting started guides. So everything that I've shown you here is documented probably slightly better over there. And there's trains, so if you're a Windows person, you can click on all the tabs for Windows information. There's various flavors of Linux, depending on whether you're Ubuntu or SUSE or Red Hat or whatever. You can go and get all the commands in the right order. There's NDCTL user guides, and that's just an evolving site for documentation. So if there's anything that you see that's missing, reach out, let us know. We'll try and document it. There's some stuff that we haven't documented yet that I'd really like to document, which is really surrounding the cloud and how to get this stuff working in the cloud. But until the cloud service providers get their boxes and expose it, it's kind of difficult to write the documentation. So what we want to do, this is action to you guys now, is we want to drive the excitement for this technology, right? I mean, it's pretty highly disruptive, right? The applications have to change. People have to think differently when using this type of technology. Whether you're a system administrator, whether you're an application developer, architect, whoever you are, this stuff's going to be different ways of thinking. The tools that we presented today exist today. Roll them into your toolbox, roll them into your development processes, your server provisioning processes, and try and feed back to us, because again, we have colleagues from all the tools here. We'd love to see how you guys are using this stuff. If there's any enhancements you want, let us know. The previous slide had some where to get helpful information from. Reach out to us. We're pretty active. If we're not traveling, we're trying to respond as quickly as possible to emails and IMs and everything else. We do work with customers directly. And we do have several programs available where we can probably get you early access to some of this stuff, either with servers that we ship to you or development clouds. We have programs for academia, that type of stuff. So this is where we would like you guys to get the ball rolling, get your applications up and running on the technology. If you need help, reach out. But we'd really want to see what you guys build. Right? I mean, there's a ton of applications that you can use. Databases are the predominant one right now, but let's see what the community as a whole can build going forward from here. So with that, I'll invite Usha back. We can take some questions, if anybody has any. You're first. Go ahead, sir.
I know the DPTK folks do a lot of meetups and things.
Yes.
Do you guys do that as well?
We would love to. Most of us, well, Usha's local here. The rest of us are pretty much based in Colorado. We would love to get into some meetups.
Look for something in the early part of 20.
All right. Thank you.